Hi, in this lesson we are going to discuss the evolution of region of interest extraction for CNNs. These algorithms are split into two main categories: classifier-based approaches that generate object proposals which are then fed into classifiers, and regression-based approaches that instead take an input image and learn class probabilities and bounding box coordinates. Following the success of AlexNet at the ILS VRC 2012 competition, the next obvious question, in addition to how to improve upon AlexNet's performance, was how does this new breed of deep neural network classifier generalize to the task of object detection? In this video, we'll look at a number of techniques that cover the history of object detection with convolutional neural networks. Regions with CNN features, or CNN, is a technique that was introduced in 2014 by a team in UC Berkeley to answer this question. In their own words, they were the first to show that a CNN can lead to dramatically higher object detection performance as compared to systems based on simpler hog-like features. Although their system is agnostic to the particular region proposal mechanism used, their paper uses an object proposal method called selective search to make about 2,000 region proposals. These proposed patches are resized to something suitable for the CNN classifier, for example 224 by 224, and then fed to the classifier. The classifier outputs CNN features, which are then fed to class-specific support vector machines for prediction. They also trained a linear regression model to predict a new detection window given the features for a selective search region proposal. This had the effect of tightening the bounding boxes around the objects. Why support vector machines and not a fully connected layer with a softmax activation function? This seems to have been more a historical artifact of the way they developed and trained their network, and the authors noted in their paper that a fully deep network would most likely work too. RCNN works well, but it is really slow. It resizes and feeds each proposal through the CNN, and it has to train different sets of models separately. The CNN feature extractor to generate the image features, the SVM classifiers to predict the classes, and the regression model to tighten the bounding boxes. This also significantly complicates training. Ross Gierschik, then at Microsoft Research, introduced Fast RCNN in 2015 to solve these problems. Firstly, it takes an idea from a different deep network called Spatial Pyramid Pooling Networks, SPP nets, to share computation to speed up RCNN. SPP nets were faster than RCNN, but they were complicated and difficult to train. They couldn't be trained end-to-end. Fast RCNN borrows the concept of using a region of interest pooling. That is, it runs the CNN once per image, and it uses that shared computation across all subsequent proposals. Secondly, it simplifies training in comparison to SPP nets by merging everything into the one network. It jointly trains the feature extractor, the classifier, and the bounding box regression in a single deep model. The SVM classifiers were replaced with a softmax later at the end of the CNN to output classification scores, and a linear regression layer was added in parallel to output bounding box regressions. The network now had two output heads, one for classification and one for bounding box regression. It also meant that the network could train end-to-end, which reduced the overall training time and increased the accuracy of the model. Fast RCNN is approximately 25 times faster than RCNN. The new bottleneck in Fast RCNN was no longer the convolutional network portion, but actually it was the generation of object proposals using selective search. A team in Microsoft Research, again including Ross Gierschik and Kaiming He of ResNet fame, introduced faster RCNN in 2015. The classifier part of Fast RCNN depended on the subportions of the pooled feature calculated by the CNN as determined by the region proposals from selective search. Faster RCNN replaced selective search with a small convolutional network called a region proposal network to serve the same function. The region proposal network generates rectangular regions of interest proposals for the rest of the network to evaluate and classify. This now meant that a single CNN could be trained and the separate object proposal stage could be eliminated entirely. How does this region proposal network work? It uses the intuition that objects within an image normally fit certain common aspect ratios and sizes. Faster RCNN has a set of such common ratios that they call anchor boxes. The original paper uses 3 scales and 3 aspect ratios to give a total of 9 boxes. At each location in the image, it uses these 9 boxes to predict the probability of that box being background or foreground, in other words, an object. Bounding box regression is applied to improve the anchor boxes at each location. In this way, RPN outputs bounding boxes of various sizes with corresponding probability scores of how likely that box contains an object of any type. These bounding boxes are then passed into the remainder of the network, which resembles fast RCNN, to generate final output classification scores and to tighten the bounding boxes. Faster RCNN is approximately 10 times faster than fast RCNN, with similar levels of accuracy. It is therefore about 250 times faster than RCNN. In 2016, the You Only Look Once method, YOLO, was introduced for CNN-based object detection. It takes a different approach to the RCNN family and poses detection as a regression problem. It takes in an entire image input and learns class probabilities and bounding box coordinates in one forward pass. It does this by dividing the image into a grid. Each grid cell predicts 2 bounding boxes and an associated confidence. The confidence represents whether the network thinks the box is foreground, an object regardless of class, or background. It also predicts the classification score of each box for every class. Then these are combined to give the probability of each class being present in the predicted box. The boxes are thresholded, and boxes of low confidence scores are pruned. YOLO's model is extremely simple and extremely fast. The model only has 24 convolutional layers, followed by 2 dense layers. It poses detection as a regression problem, so it doesn't have a complex pipeline like faster RCNN. Also, unlike region proposal-based techniques, it reasons globally about the image when making predictions, and this can actually help prevent it mistaking parts of the background for an object. With YOLO, each grid cell only predicts 2 boxes, and they can only have 1 class. This limits the number of nearby objects that the model can predict, and the model struggles with small objects that appear in groups. It can struggle to generalize to objects in new or unusual aspect ratios. Finally, it uses relatively coarse features for predicting bounding boxes. So while YOLO is much faster than faster RCNN, it isn't typically as accurate. The single-shot multi-box detector is similar to YOLO in that it is also a single network without region proposals. It runs a convolutional network on the input image once and calculates feature maps. Then it evaluates a small set of different boxes of different aspect ratios at each location in several feature maps of different scales. For each default box, it predicts both the shape offsets and the confidence scores for all classes of object. It does this by running small convolutional kernels on the feature maps. When it has its collection of bounding boxes and scores for the presence of object class instances in those boxes, it uses non-maximal suppression to produce its final detections. In the academic paper, SSD used the VGG16 network as its base detector, although other networks were anticipated also to work. It adds several feature layers to the end of the base network to predict offsets to default bounding boxes of different scales and different aspect ratios, and their associated confidences. It is faster and significantly more accurate than YOLO, approaching the accuracy of faster RCNN. We'll end with a preview of what is coming up later in the course. with one of the latest descendants from the RCNN family. Kaming He, Rosh Girshik and others at Facebook AI Research extended faster RCNN by adding a branch to predict an object mask in parallel with the existing branch for bounding box regression. They called this mask RCNN, and I think you'll agree the output is pretty impressive. We'll look at these techniques and more when we cover semantic segmentation. Perhaps at this stage you were beginning to spot the trend here. We originally had handcrafted features, which we discovered we could replace with learned features. Then we had human designed proposals, selection search, edgebox, etc., and found that we could replace these with a convolutional layer also. In machine learning, this is referred to as end-to-end, as in end-to-end learning or end-to-end training. End-to-end refers to the fact that there is no need for any handcrafted intermediary algorithms. Instead, the network is able to learn directly the solution to the given problem from the sampled dataset itself. As we'll see, we are going to shift from the problem of object classification and detection, coarsely recognizing what and where, to dense pixel-level segmentation. That is, labeling each individual pixel in an image as to the label of the class it belongs to. This is called semantic segmentation.